Welcome back, Algebra 2. We're in lesson 116. Sorry, I'm going to move some stuff around. We're going to talk about permutations for just a moment. So permutations are when you have the opportunity to arrange things or to put things in different orders. For instance, if we had the letters A, B, and C, how many different orders could we put those three letters in? And that's with just moving them around, not duplicating anything. Well, we could do ABC, we could do ACB. If we decide, if we put the B first, we could do BAC, and then we could do BCA. And if we put the C first, we could do CBA, and we could do CAB. So those are all of the different variations that we could have if we rearrange these in every possible scenario. All right, so a way to do that mathematically is called factorials. A factorial is where we calculate the total number of permutations based on the number of positions that we have and then the number of items that we have. So for instance, in this case, we have 1, 2, 3 positions and 3 letters. In the first position, we could put any one of the 3 letters we wanted to. But then when we move to the second position, we only have 2 letters left. So we could choose either of those 2 letters. But then when we get to the last position, we only have that 1 letter left, and that's it. It's the only thing that can go there. And the way we calculate this is through multiplication. So 3 times 2 is 6 times 1 is, of course, 6. We could get the same calculation by using the factorial button on our calculator, and it looks like X with an exclamation point. The exclamation point is the factorial symbol. So let me show you here. If I said 3 and I hit the X exclamation point factorial, it gives me 6. So easy peasy. It's not a hard thing to calculate on your calculator. So that is when we do not have repetition. So no repetition here. I think that's supposed to be an E. Repetition. Let me see. Yeah, it's an E. Miss Tracy is not a language teacher for a reason. So no repetition is called a factorial. That means you can't duplicate any of the letters or any of the items. So what about when we can do that duplication? Well, when we have that duplication, then we're using an ability to recreate. It has an exponent or an exponential ability. So all we're doing is using an exponent. We're using an exponent and we're doing multiplication of each space. So for instance, if I could duplicate the letters A, B, and C, I could get A, I could get B, I could get C, I could get A, I could get B, I could get, on and on and on, just changing one letter at a time, right? So how many could I get? I could get 27 different versions of this. Or I could just simply say that I have 3 letters to choose from in the first position. I have those same 3 letters to choose from in the second position. And I have those same 3 letters to choose from in the third position. And now if I multiply them all together, 3 times 3 is 9, times 3 is 27, which we all know is just 3 cubed. So if repetition is allowed, then we just take the number of items, and that is our base, and then the number of positions available becomes the exponent. Okay, so repetition allowed. Then we use exponents. All right, and that is what we call permutations. So we have a permutation with no repetition, which is called the factorial, and a permutation with repetition, which is exponential. Okay? exponential. And of course, that means we use an exponent. All right, so let's do some practice problems that are using this. Okay, so I put all 5 of these practice problems up here all at once, and I kind of shortened the language a little bit, so it's not going to exactly read the way it is in the book, but it has the meat of each problem up here. So I'm going to read it the way it is in the book so that you can see the difference in what I've written. Just, my hand was getting tired, just to be honest. In problem 1, how many different ways can the numbers 3, 5, 7, and 8 be arranged if no repetition is permitted? So how many permutations can we get for number 1? Well, if we have 3, 5, 7, and 8, we have 4 spaces, 1, 2, 3, 4. We're not repeating, so that is going to be a factorial. So that's going to be 4 exclamation point, which is the same thing as 4 times 3 times 2 times 1, and that is going to equal 24. Because 4 times 3 is 12, times 2 is 24, times 1 stays the same. 116.2. How many 4-letter signs can be made from the word equal? So we have 4 spaces, 1, 2, 3, 4, and we have 1, 2, 3, 4, 5 letters here. Now, in the book it says repetition is permitted. So if repetition is permitted, then we could just say any of the 5 letters here, any of the 5 letters here, any of the 5 letters here, any of the 5 letters here. So it's going to be 5 is the base and 4 is our exponent. So if we put that in our calculator, 5 to the 4th power is going to equal 625. Okay, let me make a note here so you can have repetition allowed for this one. So this is exponential, right? And this one up here was factorial. That's the big thing, is to figure out whether or not it is going to be a factorial problem or it's going to be an exponential problem. And that is going to be determined by whether or not repetition is allowed. So on a multiple choice quiz, you have 8 problems. Let me read it from the book. A multiple choice quiz has 8 questions, and there are 4 possible answers to each question. How many permutations of the answers are possible? So in this problem, it doesn't tell us whether or not repetition is allowed, but we can assume that it is, because if you've only got 4 answers and 8 problems, then some of the letters are going to have to be duplicated, like number 1 and number 7 might both be A, right? You know, there's going to be some duplication involved, because if not, you would run out of the letters for multiple choice. So we can assume that this is going to be 8 problems, right? So 8 spaces with 4 potential problems each, or 4 potential letters each. So 4 is our base, because that's the total number of items we have. And then 8 is the number of spaces, because that's the number of problems we have. So 4 to the 8th power, which if we plug it into our calculator, would be 65,536. So this would be an exponential problem, because repetition has to be allowed based on what it is. All right, so in number 4, how many 3-letter signs can we get from the word numeral and no repetition? If I can actually write the word repetition here we go. That's much, much, much better. No repetition, so this means it's a factorial. So that means we have 1, 2, 3, and we have 1, 2, 3, 4, 5, 6, 7. Okay, so 7 times 6 times 5. Wouldn't it be easy if we could just plug that into our calculator and come up with the factorial instead of having to do all that multiplication? There's a way to do it. And it's really not beneficial on a little number when you're just doing 3 numbers like this. Like this is just 7 times 6 times 5, 210, right? On a small set of numbers here, it's really not worth the effort. But what you can do, what works, is to take the, find the missing number here. What's the next number? That would be 4, right? So we find the 4 factorial. 4 factorial is 24, right? So we could say 7 factorial divided by the 4 factorial, which is 24, and that gives us 210. And we know that that works because of the associative property of multiplication and the inverse operation of division. We know that if we have 4 times 3 times 2 times 1 here, that's 24. So this big number here, that would have been like 5,020 divided by 24, gives us these 3 multiplied together, just because of the way math works. So that is a possibility that you can use. You can take the highest factorial, divide it by the next missing factorial, and that will give you your answer as well. Okay, so in this case, that was 7 factorial divided by the answer to 4 factorial, and that equaled 210, which is the same thing we got here. But when you only have 3 numbers to multiply, just multiply those numbers. And if you have really big numbers to multiply, it's easier just to multiply those numbers too. And I'll show you that on this next problem. Janie had 5 display places in her store window and 38 items to display. Obviously, because they're physical items, you can't duplicate them. So she has factorial properties here. All right. Because they're physical items that she needs to place in this display of her store window, and she can only use 5 of those. So that means she's going to have any one of the 38 here, any one of the 37 here, any one of the 36, any one of the 35 left, and finally any one of the 34. Now, in a situation like this, it is just as easy to multiply 38 times 37 times 36 times 35 times 34, which gives us 60,233,000, or 60,233,040. So 60 to 33 and 40 right there. Now, you could use this method here, right? But on the calculator, you have to go a little bit out of your way to do it. And I really don't advise it when you don't have but just a few numbers to multiply. When you have just a few, it works, but you have to go about it in a roundabout way. So just multiply these and be done. But if you had 20 numbers that you had to multiply, okay, that's when I would recommend it. So in this case, we have 33 would be the next missing factorial. So I would say 33 factorial. Notice it's a base 10. This has 36 more decimal places. So we're going to put this in our memory. We're going to add it to our memory. And then we're going to clear. And then we're going to do the 38 factorial and divide it by the memory recall, and that's going to equal not the same thing because apparently I didn't clear out my memory before I started. Memory recall is 0. Okay, now I can do that. 33 factorial, I'm going to add it to the memory. Then I'm going to do 38 factorial divided by my memory recall, and I get 60,233,040. But then I have a bunch of decimals. So it's not going to be exact when you have really big numbers, because you have those decimal places, that the scientific notation and the logarithm opportunities, because your calculator just can't display that many numbers. So it's going to be a lot easier when you have only, I'd say, less than 10 spaces to multiply, to just multiply them. That's a lot easier. But if you have something that, I don't know, 10 or less, let's see what factorial 10 is. Let me memory clear also. Okay, so that one's doable. Let's see, 20. So no, let's see, 15. 15's doable. 18's doable. 18. If you have a factorial 18 or less, okay, then you can do it on the calculator and it should be fine. But if you have a number greater than 18 and you've got to go to a certain point and stop, just multiply them and you'll get an easier answer than the roundabout way that I just showed you by dividing by the permutation of the next missing number. I said all that to say this. We're done with permutations and let us move on. So we've talked about probability before. The study of probability is based on the study of outcomes that have an equal chance of occurrence. And that's important to understand. Probability is solely about equally occurring events. You're using fair dice. You're not using weighted dice. You're not using special cards. Everything is an equal opportunity chance of happening. We call the set of equally probable outcomes the sample space, right? So sample space, there's some terminology there for you. That's when all your opportunities to occur are equal. So if we have a coin and we flip it, there are two equally probable chances of things occurring. We have a head side and we have a tail side. And if it's given that it's a fair coin, meaning it's not weighted on one side to flip on that side, then our sample space looks like this. All right. We could have a heads or we could have a tails as our outcome. 50-50 shot either way. We define the probability of a particular result as a number of outcomes that satisfy the requirement divided by the total number of outcomes. So the probability of getting a head on one flip of the coin is 1/2. So the probability of getting heads, we have the outcome, desired outcome here over the total possible outcomes. And we did a little bit of this last year. I hope you remember some of that. So the desired outcome would be heads, which would be one of the two outcomes. And the total possible outcomes is 2. So the opportunity to get a heads is 1/2 or 50-50. An equal opportunity here. If we roll a die, that's like a little 6-sided die, we have the opportunity to roll a 1, a 2, a 3, a 4, a 5, or a 6. And our opportunity or our probability for rolling a 5 would be 1 out of 6 possible outcomes. So that would be our result here for the probability of rolling a 5 is 1 out of 6. You see, it's kind of simple. What you want over the total possible outcomes. What we wanted was 5, and there's a total of 6 possible outcomes because there are 6 sides on a cube die. The probability of getting a number greater than 3. Let's look and see how many we have greater than 3. We have 1, 2, 3 numbers greater than 3. So 3 numbers greater than 3 out of 6 possible opportunity or 6 possible outcomes. So we have a 1 out of 2 chance of rolling a number greater than 3. And all we did was reduce our fraction. That's all we did. We didn't do anything fancy. So we see the probability of rolling a 4, 6, or -3.5 is not possible because the probability of any single event or combination of events is a number between 0 and 1 inclusive. So these are all the possibilities we could have here. We couldn't get a 0 out of 6. That doesn't happen. There's no 0 on the die. So we get the 1, we could get the 2, we could get the 3, we could get the, I don't know why I'm writing the numbers. We could get the 4, we could get the 5, or we could get the 6 of each of those. Let me erase all of this. Now, what if I have 2 die? If I have 2 die, then think back to what we just talked about with exponential permutations. If I have 2 dice, I could roll, the first dice could be 1 through 6. The second dice could be 1 through 6, right? So I have 6 possibilities for the first space and 6 possibilities for the second space. So that means I have 6 squared, or 36 possible outcomes. So that is our exponential permutation put into practice when we see dice being rolled. Now, what if we have 4 dice? If we have 4 dice that are rolling, there are 6 possible outcomes for the first dice, 6 possible outcomes for the second dice, 6 possible outcomes for the third dice, and 6 possible outcomes for the fourth dice, right? So that is 6 to the 4th power, and if we put that in the calculator, 6 to the 4th power would be 1,296 potential permutations or outcomes. So those are things that we have to think about whenever we are doing probability, is how many possible outcomes are there? Are they duplicable? Which with a dice they are, because you have 1 through 6 on each dice. And how do we apply that so that we find the total number of outcomes? All right, so let's look at a practice problem for this. Let's look at practice problem number 6. Let me clear this for us. All right, in number 6, our problem states 2 dice are rolled. What is the probability of getting A, the sum of 7, or B, a sum greater than 8? So first, let's look for the number of outcomes. Well, we know we have 6 possible outcomes here and 6 possible outcomes here. That's going to be 6 times 6, so that's 36 outcomes, right, that we have potentially. So our fraction is going to be, for A, something over 36. So now let's look at the total possibilities. I've drawn us a little chart here to show us that when the first dice is rolled on a 1, if the second dice is a 1, we have the total of 2. If the second dice is a 2, we have a total of 3. The second dice is a 3, we have a total of 4, and so on. When the first dice is a 2 and the second dice is a 1, 2, 3, 4, 5, 6, those totals. When the first one's a 3, when the first one's a 4, 5, and 6, and so on. So I have all of those written out for us. Those are all the possible permutations. And if you were to count these red numbers, you would find there were 36 possible numbers, or possible totals. So all that's, kind of laid out for you. And if you put that in your notebook on the back cover, then you have a reference to that whenever it comes up, and it will come up in problems that we have. So let's look for all of those that have the sum of 7. I'm going to use my highlighter. So we have 1, 2, 3, 4, 5, 6. 6 possible outcomes that equal 7 out of 36. We can reduce that fraction by saying 1 over 6. Right? So 1 over 6 would be our answer for A. What about B? What do we have for B? Let me use my highlighter, and I'm going to use a different color. So greater than 8. All right, let's start with 9. That's 4, 5, 6, 7, 8, 9, 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes out of 36. Ooh, I put that in the wrong spot, didn't I? So out of 36, we have 10 possible outcomes. Now we can reduce that a little bit. We can divide this by 2 and get 5, and we can divide this by 2 and get 18. So 5 out of 18 is our probability of getting a sum greater than 8 when we roll 2 dice. 10 out of 36 rolls, or 5 out of 18. All right. So let's talk a little bit about independent events. Let me clear the page for this. We say that events that do not affect one another are independent events. If Denise flips a dime and Paul flips a penny, the outcome of Denise's flip does not affect the outcome of Paul's flip. So we can say that those events are independent events. We can also say that every time that Denise flips her dime, it's an independent event from any previous flip that she has thrown. The probability of independent events occurring in a designated order is the product, which means multiplication, of the probabilities of the individual events. So whenever we have probability of something happening in a certain order, we just multiply those individual probabilities against one another. So for instance, we know that a coin either has a head or a tail, right? And if I wanted to say the probability of flipping or getting a series where I have heads, tails, heads, it would look something like this. The probability of tossing a heads on an independent flip is 1 out of 2 outcomes, right? 1 out of 2 outcomes. So the probability of me getting tails is the same, 1 out of 2 outcomes. So 1 out of 2. And then the probability of me getting a heads in an independent flip would be 1 out of 2. So the probability of me getting heads, tails, heads, that order of flips would be 1 times 1 times 1 times 1, 2 times 2 times 2, which would be 8. So getting this specific order, my probability is 1/8. I have a 1 out of 8 chance of the coin flipping it in that manner, right? So if a fair coin is tossed 3 times, what is the probability of it coming up heads all 3 times? 1 out of 2, right? Again, 1 out of 2. And again, 1 out of 2. Our answer is the same. Even though we changed what we wanted that outcome to be, we wanted heads, heads, heads now, each individual event is still the same probability, so we have the same answer. Easy peasy, guys. We did this last year in Algebra 1, and it was super, super easy then, and it is super, super easy now. It's just all about the way that you think about it. You have to think about them as independent from one another. It doesn't matter if your last toss was heads. This next toss is brand new, fresh toss, fresh roll, whatever it is, and it doesn't matter what happened before, because you just think of it as every day is a new day. Every coin toss is a new coin toss, and anything can happen. So we have one more problem. That was actually number 7 that we just did. Let's do number 8, 116.8. And now we want a fair coin is tossed 4 times, and it comes up heads each time, right? It's already happened 4 times. What is the probability that it will come up heads this next time? If you said 1 out of 2, you are correct. It doesn't matter if it came up heads 4 times in a row. It still has the same 1 out of 2 chance of coming up heads as it does to come up tails every time you toss it. All right, ladies, that is all that I have for lesson 116. I will see you in 117.